Hello, my name is Tony Broquetas. I'm going to give you a lecture on transmission lines. The objective of the lecture is being able to understand the working principles of a transmission line and being able to design transmission lines and to get the best efficiency in terms of power, transmitted power, and also use transmission lines for things like matching impedance, for example. So, what is a transmission line? Well, a transmission line is a structure formed with conductors and dielectrics, which is able to transport electrical energy and also transmit information, and it's widely used in electronic systems and communication systems. So you see here in the slide electrical energy transportation lines, telephone lines, radio frequency lines, which actually links the antennas with the receivers and transmitters. They both share the same basic principles, and they are available in every electrical, electronic, or communication system. Transmission lines propagate signals at a finite speed. This speed can be very high, speed of light actually, or close to the speed of light, but it's not instantaneous. Actually, if the rate of change of the electrical signals is slow compared to the delay introduced by the transmission line, you can just ignore it. This is what happens with typical electrical appliances, a domestic equipment, for example, but it is connected to the power supply, actually is through a transmission line. But you can just ignore it, because the delay, it's maybe some nanoseconds. This completely, can be neglected in front of the periods, which is typically around 20 milliseconds, for example, for 50 or 60 hertz signal. But for fast signals, for example, radio frequency signals or fast digital equipment signals, the delay introduced by the transmission line is not neglectable at all. And actually, if you look at the distribution of the voltage and currents along the line, it is not instantaneous. So you see the delay here. Actually, you see how the perturbations, the electrical perturbations on the line induced by this generator, actually they do propagate along the line and not in a simultaneous way, because the finite speed of propagation. There are many transmission lines, and actually a transmission line can be built with conductors and dielectrics in many different shapes, and you see here in the slide different examples of it. Maybe the most widely used is the two wire lines in power supply, in electrical applications, and also in telephonic lines communications. When the frequency is high, or when you require a very high isolation between different lines, you use a coaxial line typically in audio, video applications, and also radio frequency applications. Again, you have two conductors which are separated at dielectric, and only the shape of the geometry, if you want, of the line is changing from one example to another. Another example is the microstrip line here in the center of the slide. What you see here is actually a strip which is actually separated from a ground plane with a dielectric layer here in the middle. And this is strongly used in radio frequency circuitry, as we will see in microwave circuits. There are also some particular examples of some kind of transmission line which involve only either conductors or dielectrics. For example, waveguides are actually metallic tubes, and actually optical fibers, they don't involve conductors, for example, so the signal is guided by a dielectric structure. These are special configurations which has a particularity that they cannot transmit low frequencies, only high frequencies are possible. Okay, let's analyze a basic example of a transmission line, which is a two-wire line. What we have here is just two conductors here, which are separated with a certain distance with a dielectric. And then we want to analyze what is the evolution of the voltage and current along the line, we have to actually establish a model, an electrical model of this line. To do this is just, let's think what is actually, what do we have here? We have a conductor. A conductor has some resistance. Also, if we have a conductor, we will have a magnetic field, which is actually produced by the current flowing through the conductor. And then, okay, the resistance can be modeled by a resistor. The magnetic field can be modeled by an inductive component here. We have also a second conductor and a separation between them. So we have an electric field here through a dielectric. So this is acting like a capacitor here. We have an electric field storage here in this case. So we have to model this with a capacitor. And then we have a finite isolation of the dielectric. We have to be modeled also with a parallel conductance parameter. So we have at the end 4 parameters which describe electrically the behavior of this line. Of course, these parameters are uniformly distributed along the line, but in our purpose to model this in a simple way, we are going to use actually a discretization model when these parameters are concentrated at certain positions along a very small step or length of a line. This will allow us to actually compute what is the distribution of currents and voltage along the line. So what you see here is we have a voltage at the input, a voltage at the output, also the intensity of input and output are represented here, and we can relate them with the Kirchhoff equations of voltage and intensity, taking into account what is the voltage drop along the series elements, or what is actually the intensity distribution along these 2 parallel elements here. So when we equate here the voltage and intensity or current intensity equation, then we can actually taking derivatives, spatial derivatives, just by assuming this delta z distance can be taken very small. So we can just take a limit of delta z going towards 0. And then what we get here is a spatial change of the voltage and the current can be related with the other parameters, with current or voltage here. And what is important, these equations relate spatial changes, which is this derivative here, with time changes, which are this derivative in the second term. And that's important because that's the physical basis why this structure can actually propagate waves. To analyze this, let's take a look how these equations look like when we assume the excitation of the transmission line is sinusoidal. In this case, we assume the shape or the time evolution of this signal follows this phasor here, which defines a frequency of the signal. We have an amplitude, we have a phase represented here in the phasorial diagram, and what we have here is the same, the previous equation, spatial derivatives, and the time derivatives are just substituted by this term here, omega, in the equation. This is actually the result of a time derivative here when we assume an harmonic case. Then, if we do that, and we take second derivative of space derivative of the first equation, and we substitute the current term in the first equation, we get this voltage wave equation here, which actually relates space change of the voltage with a time change of the voltage, because at the end this term here is actually a second time derivative of the voltage along the line. The same happens with the intensity, and actually this is the reason why these structures support waves, because both space and time changes are related by a constant, and this constant here is this gamma parameter, which is the complex propagation constant, which contains actually information on the speed of propagation and the attenuation of the wave propagating along the line. And all these parameters, alpha and beta, which is the phase constant or wave number of the line, actually depend on the electrical parameters of the line, resistance, induction, capacitance, and conductance along the line. So now, if we ask ourselves what are the possible solutions for the previous wave equations, well, the answer is simple. The solutions are harmonic, again, so it's actually sinusoidal waves, but they can propagate in both directions. So we can actually, a solution, it's actually the superposition of a progressive wave that propagates from the generator towards the load, and also a regressive wave that propagates backwards from the load towards the generator. So both solutions are possible, and our general solution is actually the addition of these two components. The same happens with the intensity, so it is the same equation that holds for the voltage and for the current. Now, again, the complex propagation constant, as we have seen here, defines the relationship between voltage, current, and also the velocity of propagation, as we will see in a moment. What we have here is, for example, if we make a ratio between the voltage and intensity in the forward wave and also the voltage and current in the backward wave going back towards the generator, the relationship between them is the impedance, or the characteristic impedance of the line, Z0, a very important parameter in the line design. This characteristic impedance is related to the constitutive parameter, electrical parameters R, L, G, and C of the line. And also the phase velocity of propagation, it is also related to the constitutive parameters of the line and also to this propagation constants. A beta constant is establishing actually the phase velocity of propagation, and the wavelength is again related with the same phase velocity beta. In many cases, the transmission line losses are sufficiently small to be neglected. When this happens, the previous equation simplifies quite a lot, because now the propagation constant, which is in general a complex constant, becomes a pure imaginary number, which depends only on the L and C parameters of the propagation line. In this case, alpha is modeling the losses and is 0 because it's a lossless approximation, what we are doing here, and the beta parameter, you see, contains the frequency and the product L and C. The characteristic impedance of the line is a real number, which is just a quotient between or the ratio between L and C parameters. And then what happens is the velocity of propagation, it does not depend on the frequency, it depends only, again, on the inductance and distributed capacitance of the line, of the transmission line. The wavelength at the end, which is actually the spatial separation of a period of oscillation along the line, is actually 2 pi over beta parameter, or what is the same, the product of the speed of light by the period of the signal.